Hi everyone, welcome to our ISC 2022 webinar for this week. I hope everyone has had a good week. If you are in Singapore, you would know that we've had a bit of a crazy, intense week back in heightened alert, but I hope everyone is doing well and keeping safe wherever you are in the world. Yeah, so as usual, thank you all for joining us this evening. Today we have Dr. Burak Iskandar, who will be sharing with everyone about the basics of orbital mechanics. Dr. Burak is the founder of Final Proximity and also a researcher at NTU. But some housekeeping rules before we start, or some things to note before we start. Which is, firstly, I know some people have been messaging me saying that you have not been receiving the emails for the webinars to register. So we do realize that this is an issue. It could be a couple of different reasons. I would ask that some of you try to check either your spam, your promotions, or your socials tab if you're using Gmail or Outlook. Because of the system that we're using, the emails sometimes do end up there. Otherwise, if you're still not received, if you've checked all those folders and you still cannot find the emails, drop me a message either through email, Discord, or anywhere that you can find me with your email address, and then we will double check it against our database our backend database. So that's the first thing. Second thing, our webinars are all recorded. So yes, you will get access to them. Even if you, yes, I say this every week, they are all recorded. You will get access to them either way. We are actually planning to launch a learning platform really soon. And the webinars will all be accessible through that platform. So you won't get the issue of the expiring web links that I've been sending out through email. So just keep a lookout for that. And the third thing is, next week we do not have an ISC webinar, but in parallel to the World Space Week, we have a special Women in Space webinar hosted by SSTL that is taking place instead of the regular ISC topics. So that might be interesting for you guys if you're interested in looking more towards the industry, learning more about what people do, the different jobs in the industry, versus all these. I know we've been doing a couple of very technical sessions, so it could be a bit of a nice break. But yeah, with all the announcements said and done, I will hand it over to Burak to start his lesson or his sharing for today.
Okay, thank you, Jillian. Hello, everyone. My name is Burak. Just to say hi to you with my cams on. Today, I will be sharing the orbital dynamics fundamentals, and it will be fairly simple lecture, but I would be very happy if you guys ask your questions through the chat. Jillian hopefully will help me out, and I'll try to address them. So my voice is clear, Jillian, right?
Yep, we can hear you loud and clear. Your slides are also visible.
Perfect. Great. Okay, let's get started now. So today I will start with the history, of course, and then we will discuss the Kepler's laws from first to third, which are the famous ones. Then we will discuss the inverse square law. After that, I'll go through the orbit types and we will discuss the Keplerian elements. Later, we will see orbital perturbations and why do we care about them, how to overcome them. And we will discuss how satellites orbit. And then we will close the session with some examples and wrap up. So first of all, the two people who were crucial for today's orbital mechanics. The first one is the Kepler, who lived in the late 16th century and derived the three laws of celestial mechanics based on the astronomical observations. And today we will investigate these three laws. Secondly, Newton. After Kepler Newton derived, among many other things, the law of gravity based on the theoretical deliberations. With them, one can also derive the Kepler's law. So around 1605, the German astronomer and mathematician Johannes Kepler presented his 3 laws of planetary motion. These laws form the basis of our understanding of satellites and planetary orbits. So here we see the Kepler's first law, which simply states that the orbit of each planet is an ellipse with the sun at its focus. The point at which a planet is at its closest to the sun is called perihelion, and the point at which a planet is at its farthest from the sun is called aphelion. Following that, the second law states a radius vector joining any planet to the sun sweeps out equal areas in equal length of time. So if you look here, if this area took 1 month, then we simply say that A1 is equal to A2 if that one also took 1 month for the satellites or planets to travel. So following that, we can discuss the third law, which is even more interesting. It states that the squares of the sidereal periods of the planet are directly proportional to the cubes of their mean distance from the sun. So if you look at the Earth example, our unit is year, and our period is, of course, 1 year, and the square of 1 is 1, and mean distance is roughly 139 million kilometers, then we will call it astronomical unit. Then square of 1 divided by the cube of 1 will give us 1. And as you see here, as the mean distance and the period change, the ratio is actually still staying around 1. So we can say this is not 100% correct, but it gives us a very good understanding of how the planets actually orbit around the sun. And before moving forward, maybe we give a background of some mathematics. So I would like to ask, how would you guys define a vector?
Feel free to type your answers in the chat for this one.
Yes, please. Is there any chat?
The question was, how do you define a vector, guys?
Yeah. Yeah. Okay. Okay, great. Great, everyone is listening. Yeah. So we can even simply, let's call it a very chilled session, something with a direction and magnitude. So when we say that, we can now define a position of P with actually 3 components, which consist of X, Y, and Z magnitudes, and E1, E2, and E3 vectors. Then let a coordinate frame be defined through the 3 unit orthogonal vectors. And we can say the origin to be OB, and then we can define the frame as given. So in MATLAB, we can simply add vectors or add 3x1 matrices. But actually, MATLAB does not really know whether they are in the same reference frame or not. So when we are doing mathematical operation, please check that you are on the same reference frame. And here we have one example why we are caring about the reference frames. So this is a robot that is designed to test next generation guidance and control and navigation algorithms, and it has its own sensors. Let's say it has its own camera here, and it has its navigation sensor here, and it has its thrusters here and there, and there is the center of the reference frame, which is somewhere here. So when we say, okay, something is ahead of us 10 meters, it actually means it is ahead of its instantaneous orientation and position. But we need to do the transformation in order to see its actual position in the inertial frame. So for this reason, or if you look at here, docking with the International Space Station, we do care about the reference frames and how we define them. So here you can say that we have one reference frame here at the docking port, we have other reference frame here at the center of mass, and we have some reference frames defined here at the sensors, and there are some other reference frames here maybe defined at the thrusters. Moving forward, if you look at here, my point of this slide is notation is important. So if you want to define a vector with r over bar, it's fine. If you want to define it with bold r, it's also fine. If you want to define it with r over arrow, it's also fine. They're all good. If you want to define the distance with x, it's good. If you want to define velocity with v, acceleration with a, it's also good. But make sure it's consistent. Alternatively, what you can do is you can say, okay, I define acceleration as a derivative of the velocity. So basically, we all know that acceleration is dv over dt. So instead of that long form, you can also say, I want to define it as 3 dots. So these are all good, but believe me, guys, this is something that all professors, all researchers really pay attention when they first start reading your writings. Is it consistent? Here, I would like to also point out some examples. So consistency and using different things that mean same thing can be used, but make sure that you always start with A and you continue A. Let's say in your first page, page number 1, you are saying A is acceleration, and you go page number 14, then you suddenly change it to V dot, then the reader can easily get irritated or disappointed. So here I provided some mistakes. So the first one, we are trying to define the state vector x. So state vector consists of 3 position states, x, y, z, and 3 velocity states. But the problem here is what? Can anybody see why this notation is not correct? And share in the chat, please.
We do have a question from Ying Jie. When converting one frame to another, for example, from perifocal reference frame to ECI, how do we know the initial value of the ECI?
Oh, so I cannot see it, but if I understood correctly, this is actually a question of how do we localize our satellite? So this question actually goes back to the navigation system. So on spacecraft, you have your ears and eyes. So you look at the sun, for example, you look at the stars, and you look at the Earth, you look at the moon, and you try to localize yourself. Alternatively, if you're in a low Earth orbit, you can also use the navigation satellites, which is exactly the satellites that operate in your car on your phone in order to roughly estimate where you are. So your onboard sensors will give you that information. Otherwise, you will be a little bit lost in space. But from there, it is a matter of kinematics, how to convert from one reference frame to another one. Yeah, that was the answer.
Hopefully that answers your question, Yingjie. If you have a follow-up, you just feel free to let us know.
Yeah, so Stefan, okay, I like to, yeah, okay. Quite a few guys grasp it. So here, the problem is, as I mentioned, we have to know what we're doing. So we said X, so we defined a coordinate system. And let's say we said this is X axis, and we are here. So X is giving us this one. But this X also gives us this one. Then it creates a conflict. What are you talking about? The reader will tell you. So this should be either X over bar or bold X or X, actually this was an arrow, yeah, X over bar or bold X. So you guys are right. So similarly on the right, as you see, we have Y bold here, which is not really complying with the other notations that we have. And here we have capital Y that is also creating some confusion. And here, that's what we want. Here also can. And here also can. Yeah, it's been a while. I haven't checked them, so I'm also checking myself. So yeah, so the notation is important, especially when you're doing orbital dynamics or attitude determination and control. Please be consistent. Moving forward, inverse square law. Now let's discuss about it. When I was studying, like you guys, I experienced that the name of the formula, or in this case, a law, can be a little bit of discouraging. So I tried to guess what the formula would look like if I just don't look at it. So here, first, we know that a fraction can be made of two components, and we have numerator and the denominator. So if it is inverse, so it kind of implies to me that there are some, let's say, term at the denominator, and we still don't know about this, and this term has a square value. So that's what we expect just by seeing the title. And in this slide, let's discuss a little bit more. The idea is that you have two bodies and they're attracted to each other. We are now defining the vector from the Earth to the satellite as r with a bar on top to signify that it is a vector. So in this case, let's be aware of the notation. So the closer they are, the stronger the attraction. And the further they are away, the weaker the attraction. So attraction between two bodies is related to 1 over distance squared. That's why we actually call this inverse square law. In case of the Earth and the satellite, they each have an attractive force towards each other. The magnitude of that force is equal to the gravitational constant times mass of the Earth times mass of the satellite, let's call this S, divided by R squared. So here, I have a quick question. Why, instead of R squared, we have R to the power of 3 and R over arrow to the right? So we have this one, but we don't have this one. R is unit vector. R is not a unit vector. R is the vector from Earth to the satellite, which is a position vector. Perfect. The Sakshi Mishra actually gave a great response, but I think Priyanka meant the same thing. It's just he was Russian, or she was Russian. So it's true. We don't want to just deal with the magnitudes. We want to deal with vectors plus the magnitudes. Then we will know the direction of the force. Here, as you see, this force has a right arrow on it, just like this one. So my second question is, so this was R-cube says the reaction. No link. R-cube. Actually, yeah. R in R. So R is like X, Y, Z. R1, R2, R3. Okay. So these are the direction vectors. These are the magnitudes. So my other quick question here is, we know the mass of Earth is vastly larger than the mass of the satellite. But what are the difference between F Earth and F satellite in terms of magnitude? What can you guys say? They're the same. In terms of magnitude. Yeah, exactly. Kaiwan, you're very right. They're the same in terms of magnitude because as you see here, the F Earth and Fs, they both consist of the mass of Earth and mass of the satellite. So the magnitude are the same, but the directions are the opposite. So yeah, this also answers this question. And the third question is, why satellites do not fall on Earth then? Because of their velocity. Electrical due to centrifugal force. Okay. Okay. A lot of similar answers. We will visit this question later. But for now, let's leave it is such that the acceleration third. Yeah. Okay, a lot of interaction on the chat. Yeah. Okay, great. Thank you very much for the answers, guys. Now, when I was studying, again, I often see these kind of questions, and like, let's discuss when we, okay, so if you look at here, this is the general form of the inverse square law, which means you can sum all the accelerations acting on a satellite but we often neglect the gravitational force from the Neptune. Why? Is Neptune right? Okay, no answer, I just repeat again. So when we are dealing with a satellite around Earth orbit, we generally add Venus, Mars, Jupiter, Sun, but we are neglecting Neptune. Why do you guys think why do you think it's negligible? R is too big. Sun and Neptune, but we are talking about the satellite orbiting Earth. So it's nothing to do with Sun. Yeah, okay, for now, again, got the answer. The denominator is so high. That's why the value coming from Neptune is so low, so we can neglect it. But we are often getting Jupiter into our consideration, whereas we are not considering Mercury. Why is that? I say it's equally far from the Earth orbiting satellite. Okay. Yeah, this time Ramesh got the answer. So as you see here, our mass is also important. So Mercury has very small mass, then it's pretty much nothing compared to the effect of Earth or Jupiter. That's why we are neglecting. Okay, great. Now, let's go to orbits types. So before going into detail, let's define what orbit means. In physics, an orbit is the gravitationally curved trajectory of an object, such as the trajectory of a planet around a star or naturally satellite around a planet. And when we talk about satellite, it's a satellite. A satellite is a moon, planet, or machine that orbits a planet or a star. And today, we will call our artificial human-made objects in space as satellites. In the most basic category, we can actually define the orbits in two types: elliptic orbit and circular orbits. Moving forward, we have the altitude, which is the absolute height from the sea level. In this case, let's say this is the sun, so it's the altitude from the surface of the sun. Moving forward, we have LEO type of orbit, which stands for low Earth orbit. And it's the satellites that are orbiting at altitude below 1,000 kilometers, while medium Earth orbit is the satellites that are pretty much all of them between low Earth orbit and the geostationary Earth orbit, which is around, maybe it's too small, 35,800 kilometers away from the surface. We also have sun-synchronous orbit, which are also called heliosynchronous orbit, which is nearly polar orbit. As you see, this is the North Pole and this is the South Pole. This is the orbit. And the satellite passes over any point of the planet's surface, let's say here, at the same local time. Which means if satellite is here 6 p.m., tomorrow satellite is gonna visit the same spot at 6 p.m. So it's great when you want to do imaging or weather forecasting satellites. And lastly, geostationary transfer orbits are the intermediate step for reaching their final orbit. So from low Earth orbit to geo orbit, we have to do a transfer. And if we have a look at the illustration, the schematic of orbital altitudes and the coverage areas are given here. as you see, the LEO is very small, has very small coverage, and it's very close to Earth in terms of the altitude. And medium Earth orbit is higher orbit, it has higher coverage, and GEO has the highest coverage and it has the highest altitude among the orbits that are presented here. We also have some special orbits. For many spacecraft being put in an orbit, being too close to Earth can be disruptive to their mission, even at a distance or distant orbits such as GEO. So although we believe that this is so far, it is for some cases still very close. So the engineers have discovered 5 Lagrangian points. Those 5 points, where this is the Sun, this is the Earth, and here you see the geostationary orbit, and sorry, this is the lunar orbit. So you can see how far the Lagrangian points are. So at these, normally the 2 objects exert an unbalanced gravitational force at a point, which change the orbit of whatever is that point, right? So in other words, so if there's Sun here, there's your satellite, there will be attraction, and this orbit, this satellite is going to be pulled here and there, but at these particular points, the gravitational forces of the 2 Lagrangian bodies and their centrifugal force balance each other. So scientists take the advantage of these specific points to do better scientific missions. Secondly, we have Molniya type of orbits. And here you see the ground track of Molniya orbit. Ground track is the path on the surface of the planet directly below the satellite's trajectory. It's this one. And a satellite in this orbit spends most of the time over the northern hemisphere and passes very quickly the southern hemisphere because of the elliptic orbit behavior. So this is highly elliptic, and as you see here, and if you're familiar with the world map, it passes through USA and Canada, and also passes through some Middle Eastern countries and Russia. So if you are planning to have a single satellite that can do all these observations, this is the orbit that you need. So moving forward, we are familiar with the commonly used orbital types, and they allowed many missions to come through, which are given in this picture. Again, depending on the objective of the mission, such as navigation, science, different orbit types, as well as satellites can be selected. Now, I would like to ask you guys how big a satellite can be. So can you guys guess maybe the size or weight? Chat, I'm waiting. How large is a satellite? Please answer. 5,000 kilograms. Oh my God. Okay. 500 meter tall. Okay. GEO 1 is 1 to 3 tons, 100 kg. The moon. Okay, that's the natural one. Depends on the classification. Stefan gave a very political answer. Okay, let's go it his way. So we have satellites as large as a rhino or even larger than that. As you know, we have just stationary satellites, and they are really up to few tons, could be even 10 tons. And we have CubeSats, which are mostly designed and operated by the universities. They could be 1 kilogram, like a small duck. And recently we have picosatellites and even femtosatellites. So this is literally a human hand, and that's the size of a satellite, which is like a few grams. So from few grams to few tons, you can have a satellite. You can acquire sensor measurements in space thanks to the miniaturization of the technology. So I think someone asked a question about International Space Station. Do you guys know how large is the International Space Station? 450 tons. This time, no math, please. The length, the dimensions. Bigger than a rhino, yeah. About a football field, maybe. Okay. For now, I will go with your answer. So, International Space Station, which is the largest collaboration that has ever been made by the human beings across many countries, is larger than a soccer field, a football field. So it consists of multiple modules. And as you actually see, all these modules look like a part of a rocket. So actually, you have your own rocket, and you have the payload, and this goes in space, docks with the other one, and you, at the end of the day, assemble the International Space Station in space. One of you said satellites can be as large as you want. Actually, it's not so true. As you see, the rocket has their own fairing size, so the satellites should be fit inside the rockets. But today, scientists are looking at the opportunities to do in-orbit manufacturing. And one way is to do 3D printing or using autonomous robots to enable larger and greater structures in space. So moving forward, let's now define 3 different types of orbits again from the geometric side. And the equatorial orbit is this one, which is when the satellite rotates in an orbit directly above the equator, usually in a circular path. Inclined orbit, number 2, they are the virtually all orbits except those that travel directly above the equator or directly above the north and the south poles. And a polar orbit is when the satellite rotates in a path that takes it over the north and south poles in an orbital pattern that is perpendicular to the equatorial plane. This is the equatorial plane. This is pretty much the orbit. And I'm sure you guys know what perpendicular means. Okay, now this part is very important. Most of the time, people get confused. So attention. Here, the green ones are the size and the geometry of an orbit. Only 2 parameters, semi-major axis in terms of kilometer and eccentricity, which does not have a unit. And the orange ones are the orientation. They're representing the orientation of orbit. And the gray one is the current location point. So now let's have a look at what it looks like. So if you write the Keplerian elements to Google, this is pretty much what you're gonna get, a lot of these pictures, but it is not always very easy to understand which one is what. That's why let's watch this video, which is very short, from the University of Bristol. So as you see, the radius increasing. So now we are talking about something about the size. So semi-major axis, which is changing. Oops, sorry guys, sorry. So first, the semi-major axis, which is if it's the circular orbit, it's the radius of the orbit, and it changed the long side of the ellipse. And now we will discuss the eccentricity. So major axis getting bigger. Watch out, now it is moving to the side. Eccentricity is like the deviation of a curve or orbit from circularity. It varies from 0 to 1. 0 means perfect circle, and 1 means parabola. And in between, we will call it elliptic orbit. So here you see an elliptic orbit. Sorry, guys. Yeah. And thirdly, we will have the inclination. So the inclination changes with the angle of the orbit plane about the central body with respect to the central body's z-axis. And now we can go to right ascension of the ascending node. So here, watch out carefully. Yeah. So the right ascension of the ascending node rotates the orbital plane in the fundamental plane, or in the Earth's case, equatorial plane of the body. And moving forward, watch out this one. We are not moving, we are just rotating. As you see, the egg-looking shape is rotating. So this is the argument of periapsis. Rotates the periapsis point within the orbit plane. And finally, if you look at this shape, it doesn't tell us where the satellite is. So our satellite is here, or here, or here. We just need one more term to tell it to us, which is the true anomaly. So now the true anomaly is the satellite. For circular orbit, you can actually calculate where the satellite can be in the next minute or next given period of time. So in other words, we can keep the first 5 elements constant, and we can know the position of our satellite with one true anomaly element subject to some errors. So some of you may, do we say equator is the reference information? Yes, for now, that's correct. And for some of you, you may say that, hey, look, I know the Cartesian coordinate system, it looks much more easier than Keplerian elements. Why are we using it? Let me try to answer that. So let's say your satellite is here at time t, and this is your Earth, and this is the ECI frame you guys were mentioning. And we know that satellite will move here at time prime, let's call it T prime. Then we will need X prime, Y prime, Z prime, X dot prime, Y dot prime, Z dot prime. So we'll need 6 new elements, whereas here we keep this one, that one, that one, that one, and that one constant. We just need the true anomaly. So if you look at the V value, satellite was here at time t, and it went to here at t prime. So it is very easy for us to define where the satellite is. Now, I want to discuss the orbital perturbations. So here, I tried to calculate the orbital perturbations for 2 different satellites. One, 500 kilometer low Earth orbit satellite. The other one is the geostationary satellite, which is way farther. So as you see here, for the low Earth orbit satellite, the atmospheric drag has the most dominant effect, whereas for the geostationary satellite, there's almost no atmospheric drag. And for the solar radiation pressure, they're experiencing the same perturbation, but the effect of sun becomes more dominant for the geostationary orbiting satellites. So can you guys tell me why is this happening? And okay, Kai Wen, thank you for this question too. This is a term, let's say 6 times 10 to the power of -5 times A over M. So here, the magnitude of disturbing accelerations acting on a space vehicle whose area mass rate is to be multiplied by this constant number. So A is the area and M is the mass. I just tried to give a generic form such that you guys have a plug and play calculations. But here, with the knowledge you have now, can you comment why the effect of sun is less important to low altitude satellites, but it is more important to geostationary satellites? So -6 is greater than -7, guys, just to remind you. Tell me why the sun is less important for LEO satellites, getting closer to the sun. If you're getting closer to the sun, listen, Arif, sun is here, this is Earth, and if this is your satellite, then you're actually farther from satellite. So your satellite can be either here or here. So it keeps changing. Oh, we did. You asked very, very interesting question that I think we have to revisit that later. Now, we need to focus on why the effect of sun is more dominant for geostationary orbits. Guys, let's put the ammonia aside at the moment. Earth's gravitation is a more important role in geo. Priyanka, thank you very much. So as Priyanka says, the role of Earth is more dominant when you're approaching to Earth, whereas when you're far from Earth, the effect, because this is F Earth, some term over Earth radius from the center of mass of Earth square, right? So if this is so large and this goes down, the effect of sun, let's say 10 units, and if this term goes from 1 million to 500,000, then the effect of 10 will increase, although it is actually constant value. So yeah, Priyanka, I agree with you. Now, as a satellite developer, you have to ask these kind of questions. What do you care most for the LEO satellite? As you are doing remote sensing satellite. What do you care most for the crew transfer vehicle? Let's say you are sending some crew to space station. Or what do you care most for the small satellites that are going to the moon? Or what do you care most for the Von Allen belt probes? So I strongly encourage you to do these self-questioning and then come up with some system requirements depending on your sensors, on your mission types. And here the question is, why do we care about the perturbations? Okay, let's say, all right, there is drag perturbation, there is solar radiation pressure, there is sun perturbation, but why do we care about it? Anybody has any answer? Station keeping, especially for geostationary satellite. A great answer, Jacob. Yes, that's one of the reasons. Maybe the other reason is, let's say you have an imaging satellite that plans to target a camera to here, but because of the perturbation, there is a error in between, and you're not able to see what you want to see. Yep, all true. So here, let's now explain it verbally. Usually, the orbital perturbations represent unwanted inputs which affect the control system outputs and result in an increase of system error. And secondly, it is the job of the control system engineer to properly design the control system to partially eliminate the effect of disturbances on the output and the system error. And there is also, you're right, atmospheric drag can help in deorbiting the satellites. How about here, Devesh and everyone? Can you comment on this one? So here what we see is a space station from Russia and a small satellite or orbital altitude history. As you see, the altitude of the small satellite is decaying exponentially, whereas the orbital altitude of the space station is decaying, showing some similar trend like this one, but then it is going back. So what's happening here and what's not happening here? And Jacob, that's also true. Your friend, okay, Jacob says Mir is spinning out from where it is supposed to be. Anybody has any other answer? Mir using reaction control system to keep yourself define our look reaction control systems. Can you elaborate more on that space weather influence? Okay, I think you have read too much of space weather, Stefan. But unfortunately, that's not that dominant. So here you see 2 months. Oh, sorry, 2 years. Yeah, so it's just 2 years of altitude history, and this is probably like 6-7 months here. Moon's gravity pulls it backwards, maybe. Okay, think about the previous slide. What's dominant? Jacob, you tell the answer. Effect of G2. Air resistance. Okay, Kaiwan, that's pretty true. The atmospheric drag. So here we see that the atmospheric drag is the most dominant perturbations for our low Earth orbit satellite. So one takeout from this slide is we often think that space is empty and atmosphere ends like 50 to 100 kilometers. But actually, even at 500 kilometers, there is still the residual of the atmosphere. And this atmospheric drag is the most dominant perturbations ever. So the atmosphere is not 100 kilometers or 50, but you can say it is maybe up to 750 kilometers still effective here. So actually what's happening here, one of you mentioned that reaction control systems. So this is a satellite, you just develop it and rocket brings it to the altitudes and the trajectory, the altitude and the orbit it should be. But by the time the decay is effective, it has no control authority to correct it. Whereas I would disagree with this, losing the control, spinning off. Whereas here, Mir is losing the altitude and it's activating its own thrusters to go back to the altitude which is desired. It keeps decaying and it goes back. So those jumps are actually like 1-2 days of maybe thrusting event that brings them back to the original or desired altitude. So we usually don't like the orbital perturbations because they're misorienting us and increasing the system error. But as one of you mentioned, orbital perturbations, which is one of them, atmospheric drag, can be also used for the sake of sustainability of space by bringing the satellite down to the atmosphere to burn it there and clean the space, just air resistance. So space station sometimes using automated transfer vehicle to boost itself. So this is going from Earth and docking with the space station and boosting the orbit of the space station. And it has its own modules that has the thrusters that are in circle to make these operations. And another thing is, this is for the position, but it can also create misorientation, as we discussed. Since we mentioned a few of them, I want to go through one of the orbital perturbations. Then you can understand, and you can even do your own calculations how to calculate the atmospheric drag and the corresponding torque acting on the body. So let's say our satellite is like a box that is traveling with a velocity of v, and there is the air density of rho, and it has this cross-sectional area that we call A. And since it's a uniform body, let's say this is the central pressure here, and the drag force will act along this point. And this satellite also has a center of mass. Central pressure is about the shape, whereas the center of mass is what's happening inside. So maybe you have some gaps here, then the center of mass goes down. Then there's a difference between center of mass and center of pressure, which are Cm and Cp. And if you remember the right-hand rule, the moment arm cross product, the force will give us the torque. So in that direction, there will be an atmospheric torque. So which means you want to, again, look here, but there's, let's say, some wind coming on, and it's rotating your satellite, and you're actually now looking here, which is something you don't want. So how do we calculate it? Atmospheric drag, 1/2 times rho is the density, CD is the drag coefficient, times the cross-sectional area, times the velocity, to the power of 2. So here, as you see, this is not a linear curve like this. It's an exponential decay. And the reason is the drag is directly proportional with the velocity square of your satellite. So this will give you the force, and if you multiply it by the distance, this distance, it will give you the torque. So all these perturbations are actually creating a torque that will misorient your satellite. So now let's have a look at the design requirements. As I mentioned, as an engineer, scientist, you have to always focus on what are the dominant factors and the requirements of your mission. So let's say you have a satellite that looks like a Earth's selfie, yeah. Then you want to image Singapore, and you design a satellite. This is, by the way, from my university, and your boss or your customer will probably ask, can you image Singapore? Then you check your pointing accuracy, then you see that, okay, I am actually pointing with 3-degree offset. So which means, again, this is Singapore, and that's where I am. Okay, this is 3-degree. This is target. So is it enough? Then this, you need to make a calculation. So if Singapore is that large, you're looking here. So you need to go closer with the same accuracy. If you're lower altitude, you are actually qualifying for this mission, but maybe you're not for higher altitude. That's why we send our satellite to 550 kilometer, but not 1,000 kilometer. That's one way of doing that. Another research that I did for spacecraft rendezvous and docking missions, when you're approaching a target, you need an algorithms that are able to realize all these no keep out zones. So if your satellite is approaching from here, then maybe you crash with your satellite, your target satellite's solar panels. So that's not something that you want. Or you may have your own sensors, as we discussed. The in-orbit robots they're equipped with all these sensors, and they need to operate and they need to keep the target within the field of view. So all your algorithms must respect these constraints. Alternatively, if you design a CubeSat to go to the moon, then as the name speaks, CubeSat is like 1 to 10 kilogram, 1 to 10 kg. So it is very small, which means you have a limited fuel. And we also know that satellites are not going to live forever. They have lifespan. So you need to design a satellite that is able to detumble and communicate with Earth. And if the rocket gives you high energy that will fly by moon, you also need to avoid the flyby. But when you avoid the flyby, you don't want to go back to Earth, or you don't want to go somewhere else. What you want is be captured by the moon. And finally, you need to correct your orbit in order to make the meaningful measurements. So this was my previous work, but in a nutshell, these are the things that we care. So the duration is taking almost 1 year, 355 days. And the delta V is almost 1,000. So you have to make sure that this number is something that can be fit inside your CubeSat in terms of the fuel consumption. And for the duration, this number must make sense when it comes to lifespan of your components. Lastly, when you design a Van Allen probes, you also need to ask these questions to yourself. What are the problems that the satellite will experience when it goes in and out of all these inner and outer radiation belts? So ask yourself these questions, and if you come up with some challenge, you can email me and we can discuss. And here you see the objectives of the previous Van Allen belt, and you can also read what are the technical challenge they faced. So back to the questions. Most of you mentioned that this is the velocity. So I would agree, but if I were to give you a response why satellites do not fall on Earth, but they stay in their orbit. When rockets launch our satellites, they put them into orbit in space. There, gravity keeps satellites on its required orbit in the same way that the gravity keeps the moon in orbit around the Earth. So it's like throwing a ball from your door. If you throw it fast enough, it can actually go inside orbit. But because the atmospheric drag is so large, this may not really happen. It's exactly the same as what people thought once upon a time. Now, we can derive how satellite is orbiting by looking at the Newton's gravitational law and as some of you mentioned, the centripetal force. So we have learned that the net force acting on the satellite from Earth is this one. And as the satellite is moving in an orbit, it has a velocity, orbital velocity. And as Zico mentioned, we have F centripetal force, then Fc can be calculated by m times v squared over r. And if Fc is equals to Fs, then the satellite is going to keep going. Then we also know that the Fs is me and m over r2, r of 2. And this will cancel out, and this will also cancel out. So we can obtain the velocity of a satellite by g m Earth over r. Does anybody know how fast is a LEO satellite? LEO, let's say, at 400 kilometers. 7.89 kilometers per second. Okay, cool. Yeah, that's pretty much true. I think it also depends the altitude, but it is super fast. So 7.89 is like less than, let's say, less than, to be safe, 30,000 kilometers per hour, which is another unit that we are more familiar. So it's like 30,000 times faster than a fighter jet. This webinar for starters. So in summary, we can obtain the orbital velocity from this relationship. And this one, how we derive is, as you know, we are talking about the circular orbit, and the distance is velocity times t, and here the distance is 2pr, as we're talking about the circle. Then we can actually go 2pr over v in order to find the period of our satellite. About 5-10 minutes. Okay, Jalen. So you can also go and check the escape velocity. So if you're also designing a mission, you don't want it to be so fast to reach your altitude or target. So do this, and you can also make calculation by your own. 2 satellites have crashed recently, and their speed of crash is 42,000 kilometers per hour at altitude of 789 kilometers, which is like more than 20 times of F-22, F-35 fighter jet, sorry, 35, not 22. So they crashed and they resulted in thousands of space junk, as you see here. So if you're curious about this, just remember the previous findings we have and make the calculation by your own. And what is the period of geosatellite? Do by your own again. And what is the altitude of geosatellite is something that now we can calculate. So previously I mentioned that it is 37,800 kilometers, something like that. Now we know that it is synchronized with Earth. So we know the period is 24 hours. So from period, just like back in the time, how the scientists do yourself and obtain how far the satellite should be in order to synchronize with the period of Earth. And similarly, you can also, you know the distance, or you know the period of Earth, and you can now also calculate the velocity of Earth around the sun. And now I like to ask few questions. Yes, Devesh, it's true. My mistake. Sorry. The closer to the central body, the faster the satellite. Is that true? True. Okay, true. Awesome. Speed of a satellite in a circular orbit is constant. True. Okay. So now I need you guys to calculate this. Maybe you do it at home. If the satellite has 2 hours of orbital period, so T equals to 120 minutes, 2 hours. And let's say initially it is at 15 degrees. And where will it be after 30 minutes? Do this also at home. And now you guys are, I think, very confident why satellites do not fall down. And here, another discussion, but we already did this. Yeah, so I would like to close the session with some suggestions. If you guys want to know more, first thing you should do is to play games, okay? You guys play games, you guys learn space. After that, please go through linear algebra. As you see, in orbital mechanics, we are really particular with the linear algebra, all these vectors and operations. So this lecture will give you one of the best online free course available. And this book is also an amazing one. And following that, go to edX website and follow this course. It's also great. And you get to receive the course from this astronaut. So it's a great experience. And in the later stage, you can follow this 4-module course on the Coursera, which is another platform. And finally, 2 weeks later, if I'm not wrong, there will be another instructor talking about the GMAT. What you guys can do now is go to GMAT YouTube website and learn step by step how to do simulations on GMAT if you're interested. And if you want to do some readings, these are all the resources that I used to compile this presentation. And that's it, guys. If you have more questions, please feel free to ask. It's a bit longer than we planned. Sorry for that, but I hope you guys enjoyed. Okay, Jillian, that's all.
Thank you, Burak. No worries about the timing. We do have a couple of questions from the participants. So the first question is from Pranav, and they are asking what kind of orbit is ideal for probes or satellites investigating the Van Allen belts?
Okay, I think this question is quite useful, but as an instructor, I would like to challenge you to do these research by your own after having the glimpse of how I approach to identify the problems of a mission that I have no clue. So please go through the Google, ask the questions that I try to ask and reply with the examples that I provided here. And if you still don't have any answer, we can discuss. If you have an answer with suspicion, we can still discuss. But for now, I think it would be great if you guys spend some time on your own to reply this question.
Yeah, if you come up with an answer, we can discuss it a little bit if you want to type it in the chat. But yeah, there are multiple options for this. Motara asks, will space weather have an effect on satellite timings? Will it cause a slowdown or things like that?
Actually, it does. affect a lot. And in fact, just to be more precise in my answer, I'd like to show you here. This is a small star. So this small star actually means that the atmospheric drag, even the atmospheric drag, is dependent on the level of the solar activity. So the answer is surely yes.
So I think, and since you mentioned drag, coincidentally, the next question is, how can we calculate the atmospheric drag for GTO? Or in other words, how do we determine the trajectory decay for GTO?
Actually, we have discussed that. I think this question was asked before. So please go to slide number 25 when you have the slides. And this will give you the way to calculate the atmospheric drag work. If you remove this term, 1/2 rho drag coefficient times the cross-sectional area times the velocity square will give you the force. How to find the velocity, we already learned about it. And how to find the coefficient. This, I think you need to go to lookup table. You can write drag coefficient of a small satellite or the satellite you have, but to be more specific, every satellite has different drag coefficient. So you can actually think of it like this. You have a satellite that looks like, let's say, that looks like this, and you have another satellite that looks like this. So the drag coefficient 1, drag coefficient 2, let's say, and this will be smaller than the drag coefficient 2. So depending on your shape of your satellite, this drag coefficient will change. And again, depending on your altitude, the density will change. So for density drag coefficient, you need to Google. For the area, you can calculate it's the cross-sectional area. It must be perpendicular to the motion. And for velocity, you can calculate as well. This is how you calculate. And for the rest, I think you can do your own search again, how to calculate solar radiation pressure and put the terms here and there or here, and then obtain the force.
Maybe just to clarify for people who in the chat or who are attending is that I know this looks like very intimidating formulas and a lot of math and things like that. But in essence, Space Challenge just needs you to understand the concepts that you're working with. Of course, if you are able to support the concepts with calculations and formulas, that's amazing. But as long as you can understand the concepts that have been shared here today, because I know not everyone here might be an engineer or a scientist or at that stage yet, as long as you can justify the concepts to a certain extent, you are good. So you just need to understand the formulas are especially handy to come in when proving what you are trying to calculate or what you're trying to simulate. But yeah, don't worry too much. And anyway, that we have our instructors to guide you guys along the way anyway. But yeah, Burak, would you be okay to share your email for further questions from any of the students or anyone who might be interested in discussing something?
I did it at the beginning, but just to repeat the slide. Yeah.
Yeah, so you can reach out to Burak at either of his emails. But yeah, oh, Sakshi has one final question. I guess we can take this final question. When choosing the different types of orbit for satellite affect the interference they make about the measurements of electric field of sorry, can choosing different types of orbit for the satellite affect the interference they make about the measurement of electric field of the Van Allen belt?
Yes. So the closer you are, probably you get more accurate results. So regarding that, I think maybe going through more technical papers that are investigating purely the van Allen balance and the measurements for your sensors can be more helpful, but the quick answer would be yes.
Right. Okay. But yeah, I think that is it for today's session. Thank you everyone for joining. And of course, thank you to Dr. Burak for that insightful sharing. It was great as always. Jacob does say maybe we can look at Juno mission to measure Jupiter's radiation belt as well. So yeah. Is there any other questions in the chat? No, I don't think so. But yeah, thank you everyone for joining us this evening. Before you guys go, as I mentioned, next week we have a special webinar for the Women in Space because next week is World Space Week. If you guys didn't already know, it's a very exciting week around the world where everyone is celebrating space and all its space tech and science and engineering. And the theme for this year's World Space Week is Women in Space. So SSTL is hosting, instead of our regular ISC webinars, we are actually hosting a special Women in Space webinar where we will have panelists from AWS, Amazon Web Services, Maxar, Israel Aerospace Industries, as well as Dr. Sandra Kaufman from NASA, and as well as Ms. Siti from the Network Integrity Assurance Technology. So it'll be a diverse panel. We'll be discussing topics about what it's like working in the industry, giving some examples of from their own personal stories and things like that. So it should be quite an exciting one. And as Burak mentioned, Dr. Burak mentioned, is that 2 weeks from now, we'll be hosting a GMAT workshop. So a workshop for the NASA Mission Analysis 2 by a professor from the University of Tokyo. So if you are interested in actually learning how to apply everything that Dr. Burak has taught today into an actual tool, feel free to join us for that. That one will be a bit more hands-on and will definitely be quite interesting for people who are interested to go more into this topic. But yes, I believe the link has been shared in the chat, so feel free to register for that. Yeah, and I think if everyone can give a thank you to Dr. Burak for his sharing today, it was very informative. We will share the slides and the recording with everyone in the coming week, so you can look out for that if you want to look back on it. So thank you, everyone, and I hope you have a very good weekend. And thank you to Dr. Burak again for the sharing.
Thank you, Gillian, for inviting me. It was really, really a pleasure for me. Thank you, everyone, for all these interesting questions. Please don't hesitate to text me. And as Gillian mentioned, after the GMAT sessions, if you guys want to design your own mission, I have prior experience on GMAT as well, especially the work that I presented has been done in GMAT. So you guys can still contact with me regarding your mission design and we can have discussion more in depth. So thank you guys. Have a nice day. It was really great meeting you all. Good luck.
Thank you, everyone.